Good afternoon, I'm Victor Petrosky, and I'll present Space Hopper, a crowdsourcing approach to designing interplanetary trajectories. Space Hopper is a new experiment developed at the Advanced Concepts team in the European Space Agency, which, with the help of online communities, will attempt to improve automated trajectory design methods. Space Hopper is based on the problem from the 6th edition of the Global Trajectory Optimization Competition, or GTOC 6. It was formulated last year by NASA's JPL. The goal was to design a trajectory that maps as much as possible of the Galilean moon's surfaces in a given time frame. The moons were represented as soccer balls divided into 32 faces, each with a given score, from 1 to 3, and with double points for faces on Europa. The problem was very constrained and required accurate representation of the spacecraft dynamics and orbital mechanics. Such problems are relevant to missions currently being evaluated by ESA and NASA, such as the Jupiter Icy Moon Explorer and Jupiter Europa Orbiter. The GTOC 6 problem is very complex in itself. It's a 500-dimensional continuous box-bounded global optimization problem with 10 to the power 269 of possible moon phase sequences to choose from. There's also a 10-year launch window. In fact, Space Hopper adds on to the complexity of the problem compared to GTOC 6 by allowing the human players to adjust and re-optimize parameters and their bounds during gameplay. The best solution found to date for the GTOC 6 problem is 316 points out of 324 possible points. It was found by the ACT after GTOC 6 has finished. It was done through a technique called moon hopping, which is rapid transfers between moons rather than fully mapping one moon after moving to the other. As mentioned before, Space Hopper is a crowdsourcing experiment. Crowdsourcing has been a very popular trend in computer science over the recent years, and it was showing very good results as well. It's used in various different domains such as biology, astronomy, data processing, and so on. The flagship for crowdsourcing experiments for science, Foldit, has enabled scientists to model an AIDS-causing monkey virus for further research. Just after 10 days after releasing the data online, the online community has modeled the protein, whereas scientists were stumped for 15 years before. This enabled further research into AIDS. Let me now move on to Space Hopper's design and implementation. Space Hopper is an application which allows human users to design feasible spacecraft trajectories around the Jupiter system. And the players are immersed in fluid and enjoyable 3D environment. And the graphical interface gives the experiment a game-like look and feel, which means the players will be interested and will play for longer. Therefore, we will collect more data. The experiment is released online in order to reach as many potential users as possible, and again, therefore, collect more data for our experiment. All the complex calculations, such as orbital mechanics calculations or parameter optimization, are obscured from the players in order to encourage users with absolutely no astrodynamics knowledge at all. There are two goals of Space Hopper. First one is the demonstration of the state of automated design trajectory methods, and to prove that currently even non-expert human players can design complex 3D interplanetary trajectories. The second goal is even further advancing automated trajectory design methods, using data collected from human players to formulate a new tree search algorithm with new heuristics for even more efficient tree traversal. The fact is that for trajectory design, the search space grows exponentially and quickly becomes too large to fully explore even with the best current algorithms. Therefore, a new efficient algorithm needs to be devised. Space Hopper was built utilizing multiple technologies and techniques. First of all, it was built as an HTML5 application for cross-platform compatibility and online usability. The 3D graphics were done with a compact yet powerful 3D engine called 3JS, written in JavaScript. PHP and MySQL handle data storage and transfer. The flyby parameter optimization was done with self-adaptive differential evolution, or JDE, in order to ensure efficiency and accuracy. The environment in SpaceHopper is very realistic. It was all based on PyKit, an open source Keplerian calculation toolbox, in order to ensure accuracy. The visualization shows real 3D trajectories with true propellant use and flyby parameters. All celestial bodies, planets, and moons are accurately represented with real visualization and physical characteristics for calculations as well. The project relies very heavily on artificial intelligence in order to compensate for the lack of knowledge in space sciences from the users, and also to be able to hide the calculations behind the graphical interface. As mentioned before, JDE is utilized for parameter optimization. For each leg of the trajectory, the parameters are formulated into a chromosome, a four-dimensional array, with beta, which is the flyby angle of the periapsis, RP, which is the altitude of the flyby, eta, which is the timing of the deep space maneuver, and tau, which is the duration at that particular leg. These four parameters enable to provide the lowest possible delta V after JDE has evolved it properly. This chromosome is evolved for every single leg, with the exception of the incipit phase. During the incipit phase, the chromosome is slightly different. There's T0, which is the starting epoch of the whole tour, U and V, which are the coordinates of the starting point of the tour on a sphere of radius 1000 Jupiter radii, and tau, which is the same as the previous one, which is the duration of the leg from 1000 Jupiter radii to the first visited moon. The solutions are saved as decision trees, where each node represents a value of an interplanetary trajectory, and the depth represents the number of flybys. At each node of the tree, it contains a position of the spacecraft, the epoch, the velocity of the spacecraft, the cumulative velocity change, and the list of all previously visited moon phases. In order to learn the reasoning behind the human players, we need to collect as much in-depth data as possible. Therefore, the whole tree explored during the game is saved, even the branches which do not feature in the final solution, but were still explored during search. The players' backtracks are recorded in order to better understand the human search techniques and the reasoning as well as decision making. The whole collected data should provide a very interesting information on the mix of breadth first and depth first search in human reasoning, and also other innate human heuristics which could improve tree search in general. The tests of SpaceHopper has proven that humans have certain abilities which can be very useful in improving tree search, and that they can adjust and adapt very quickly in order to learn how to design trajectories in order to get a feasible trajectory and a low delta V score. Many trajectories already created with SpaceHopper by non-experts have actually surpassed the expert solutions submitted for the GTOC 6. In fact, the preliminary tests have shown that humans playing naively are able to achieve scores of 200 points and above. That puts them in 6th place for the GTOC 6 competition. To conclude, the SpaceHopper is the first crowdsourcing 3D design experiment online, It allows non-expert humans to design real and feasible trajectories, which will then be analyzed by us. It demonstrates the state of automated trajectory design methods and attempts to improve them with innate human problem-solving skills, which are very useful for new tree search algorithms and heuristics. It was also proved during testing that online players can actually outperform GTOC6 experts. And it is also relevant for future Jupiter-bound missions by ESA and NASA. For future work, there is the analysis of patterns in the collected data from humans, and also formulating a new human-powered tree search algorithm along with new heuristics, and comparing them with currently existing algorithms for tree traversal. Thank you, and let me now show you the demo of the game.